Hello everyone. We have been talking about data structures for some time now. As we know, data structures are ways to store and organize data in computers. So far in this series we have discussed some of the data structures like arrays, linked lists, and in last couple of lessons we have talked about stack. In this lesson we are going to introduce you to queues. We are going to talk about QADT. Just the way we did it for stacks, first we are going to talk about queue as abstract data type, or ADT. As we know, when we talk about a data structure as abstract data type, we define only the features or operations available with the data structure and do not go into implementation details. We will see possible implementations in later lessons. In this lesson we are only going to discuss logical view of queue data structure. Okay, so let's get started. Queue data structure is exactly what we mean when we say queue in real world. A queue is a structure in which whatever goes in first comes out first. In short, we call queue a FIFO structure. Earlier we had seen stack, which is a last in first out structure, which is called a last in first out structure, or in short LIFO. A stack is a collection in which both insertion and removal happen from the same end, that we call the top of stack. In queue, however, an insertion must happen from one end, that we call rear or tail of the queue, and any removal must happen from the other end, that we can call front or head of the queue. If I have to define queue formally as an abstract data type, then a queue is a list or collection with the restriction or constraint that insertion can be and must be performed at one end, that we call the rear of queue or the tail of queue, and deletion can be performed at other end, that we can call the front of queue or head of queue. Let's now define the interface or operations available with queue. Just like stack, we have two fundamental operations here. An insertion is called enqueue operation. Some people also like to name this operation push. Enqueue operations should insert an element at tail or rear end of queue. Deletion is called dequeue operation. In some implementations people call this operation pop also. Push and pop are more famous in context of stack. Enqueue and dequeue are more famous in context of queues. While implementing, you can choose any of these names in your interface. Dequeue should remove an element from front or head of the queue, and dequeue typically also returns this element that it removes from the head. The signatures of enqueue and dequeue for a queue of integers can be something like this. Enqueue is returning void here, while dequeue is returning an integer. This integer should be the removed element from the queue. You can design dequeue also to return void. Typically a third operation, front or peek, is kept just to look at the element at the head, just like the top operation that we had kept in stack. This operation should just return the element at front and should not delete anything. Okay, we can have few more operations. We can have one operation to check whether queue is empty or not. If queue has a limited size, then we can have one operation to check whether queue is full or not. Why I'm calling out these alternate names for operations is also because most of the time we do not write our own implementation of a data structure. We use inbuilt implementations available with language libraries. Interface can be different in different language libraries. For example, if you would use the inbuilt queue in C++, the function to insert is push, while in C# it's enqueue. So we should not confuse. I'll just keep more famous names here. Okay, so these are the operations that I have defined with QADT: enqueue, dequeue, front, and is empty. We can insert or remove one element at a time from the queue using enqueue and dequeue. Front is only to look at the element at head. Is empty is only to verify whether queue is empty or not. All these operations that I have written here must take constant time, or in other words, their time complexity should be big O of 1. Logically, a queue can be shown as a figure or container open from two sides. So an element can be inserted or enqueued from one side, and an element can be removed or dequeued from other side. If you remember stack, we show a stack as a container open from one side. So an insertion, or what we call push in context of stack, and removal or pop, both must happen from the same side. In queue, insertion and removal should happen from different sides. Let's say I want to create a queue of integers. Let's say initially we have an empty queue. I will first write down one of the operations and then show you the simulation in logical view. Let's say I first want to enqueue number 2. This figure that I'm showing here right now is an empty queue of integers, and I'm saying that I'm performing an enqueue operation here. In a program, I would be calling an enqueue function, passing it number 2 as argument. After this enqueue, we have one element in the queue, we have one integer in the queue. Because we have only one element in the queue right now, front and rear of the queue are same. Let's enqueue one more integer. Now I want to insert number 5. 5 will be inserted at rear or tail of the queue. Let's enqueue one more. And now I want to call dequeue operation. So we will pick 2 from head of the queue and it will go out. If dequeue is supposed to return this removed integer, then we will get integer 2 as return. Enqueue and dequeue are the fundamental operations available with queue. In our design, we can have some more for our convenience, like we have front and is empty here. A call to front at this stage will get us number 5, integer 5 as return. No integer will be removed from the queue. Calling is empty at this stage can return us a boolean false, or a 0 for false and 1 for true. So this pretty much is how queue works. Now one obvious question can be, what are the real scenarios where we can use queue? What are the use cases of queue data structure? Queue is most often used in a scenario where there is a shared resource that's supposed to serve some requests, but the resource can handle only one request at a time. It can serve only one request at a time. In such a scenario, it makes most sense to queue up the requests. The request that comes first gets served first. Let's say we have a printer shared in a network. Any machine in the network can send a print request to this printer. Printer can serve only one request at a time. It can print only one document at a time. So if a request comes when it's busy, it can't be like, I'm busy, request later. That will be really rude of the printer. What really happens is that the program that manages the printer puts the print request in a queue. As long as there is something in the queue, printer keeps picking up a request from the front of the queue and serves it. Processor on your computer is also a shared resource. A lot of running programs or processes need time of the processor, but the processor can attend to only one process at a time. Processor is the guy who has to execute all the instructions, who has to perform all the arithmetic and logical operations. So the processes are put in a queue. Queues in general can be used to simulate wait in a number of scenarios. We will discuss some of these applications of queue in detail while solving some problems in later lessons. This is good for an introduction. In next lesson, we will see how we can implement queue. This is it for this lesson. Thanks for watching.